Deep beneath the Swiss-French border, buried under hundreds of feet of ancient bedrock, lies a machine so powerful, so impossibly complex, that it represents humanity's most ambitious attempt to understand the fundamental nature of reality itself. This is the Large Hadron Collider at CERN, a 17-mile ring of superconducting magnets where particles are accelerated to 99.9999% the speed of light before being smashed together with such tremendous force that the resulting collisions recreate conditions that haven't existed since fractions of a second after the Big Bang itself. For decades, this technological marvel has been probing the deepest mysteries of the universe, searching for answers to questions that have haunted physicists and philosophers alike. What is the universe made of? How did it come to be? What forces govern its behavior? And perhaps most fundamentally, is our understanding of reality actually correct? Or have we been missing something crucial all along? Now, after years of meticulous analysis of trillions upon trillions of particle collisions, scientists at CERN have uncovered something that nobody expected. Something that doesn't fit into our carefully constructed models of how the universe works. They've found anomalies, unexpected behaviors in the fundamental particles that make up everything we know. These aren't just minor discrepancies that can be explained away with a few tweaks to existing theories. These are cracks in the foundation of modern physics itself, hints that our entire understanding of the universe may need to be completely rewritten. What makes this discovery so profound, so potentially revolutionary, is that it strikes at the very heart of what physicists call the Standard Model, the crown jewel of 20th century physics. The theoretical framework that has successfully explained virtually every particle physics experiment for the past 50 years. This elegant mathematical structure describes the fundamental particles that make up matter and the forces that govern their interactions. It predicted the existence of particles that were later discovered, calculated the outcomes of experiments with stunning precision, and seemed to provide a complete picture of the subatomic world. But the Standard Model has always had problems. Uncomfortable questions it couldn't answer, phenomena it couldn't explain. Why does the universe contain more matter than antimatter? What is dark matter made of? Why do neutrinos have mass when the Standard Model says they shouldn't? Why is gravity so much weaker than the other forces? These questions have nagged at physicists for years, suggesting that the Standard Model, as successful as it has been, is incomplete, that it's only part of a larger, more comprehensive theory we haven't discovered yet. The anomalies emerging from CERN may finally be pointing the way toward that larger theory. They're showing us where the Standard Model breaks down, where reality refuses to behave according to our expectations. And in doing so, they're opening up the possibility of an entirely new understanding of the universe, one that could revolutionize not just physics, but our entire conception of what reality fundamentally is. To understand why these findings are so significant, we need to appreciate just how successful the Standard Model has been, how thoroughly it seemed to explain the subatomic world. Imagine you're trying to understand how an incredibly complex machine works, something with thousands of moving parts all interacting in intricate ways. You carefully study each component, figure out how they connect to each other, develop mathematical equations that predict their behavior, and then, miraculously, your predictions work. Every time you test the machine under new conditions, it behaves exactly as your equations say it should. That's essentially what the Standard Model has done for particle physics. It tells us that everything in the universe is made of just a handful of fundamental particles. There are quarks, which combine to form protons and neutrons in atomic nuclei. There are leptons, which include electrons and their heavier cousins, as well as elusive neutrinos. These matter particles interact through fundamental forces, carried by force-carrying particles called bosons. The electromagnetic force is carried by photons, the same particles that make up light. The strong nuclear force, which holds atomic nuclei together, is carried by gluons. The weak nuclear force, responsible for certain types of radioactive decay, is carried by W and Z bosons. And then there's the Higgs boson, discovered at CERN in 2012, which gives other particles their mass through interactions with the Higgs field that permeates all of space. This framework has been tested in countless experiments over decades. Physicists have smashed particles together at higher and higher energies, looking for deviations from the Standard Model's predictions. Time and time again, the model has passed these tests with flying colors, its predictions matching experimental results to mind-boggling precision. Some quantities have been measured and calculated to agree to better than 1 part in a trillion, making the Standard Model one of the most precisely verified theories in all of science. Given this spectacular track record, you might wonder why physicists are so eager to find problems with it, why they're actively searching for cracks in such a successful theory. The answer is that despite its successes, the Standard Model is clearly incomplete. It doesn't include gravity, the force that dominates the large-scale structure of the universe. Einstein's general relativity beautifully describes gravity, but it's completely separate from the quantum mechanical Standard Model, and all attempts to combine them into a unified theory of quantum gravity have failed. This suggests we're missing something fundamental about how nature works. Even more puzzling, astronomical observations have revealed that the matter described by the Standard Model, everything made of quarks and leptons, accounts for less than 5% of the total mass and energy content of the universe. The rest is dark matter and dark energy, mysterious substances that we can detect only through their gravitational effects, but which don't interact with ordinary matter in any way the Standard Model can explain. We're literally in the dark about 95% of the universe. Then there's the matter-antimatter asymmetry problem. According to the Standard Model, the Big Bang should have created equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other in a burst of energy. If the universe had started with equal amounts of both, they should have completely annihilated, leaving nothing but radiation. Yet here we are, made of matter, living in a universe full of matter. Something must have caused a slight imbalance, creating just a tiny bit more matter than antimatter. The Standard Model can't explain what that something was. These problems have convinced physicists that the Standard Model must be embedded in some larger, more comprehensive theory, just as Newtonian mechanics turned out to be a special case of Einstein's relativity. For decades, they've been searching for signs of this new physics, looking for places where the Standard Model's predictions fail, where reality behaves in unexpected ways. They've built bigger and more powerful particle accelerators, developed increasingly sensitive detectors, analyzed mountains of data, all in hopes of finding some deviation, some anomaly that would point the way forward. The Large Hadron Collider represents the pinnacle of this effort. When it first turned on in 2008, expectations were sky high. Many physicists hoped it would discover not just the Higgs boson, but a whole zoo of new particles predicted by theories attempting to extend the Standard Model. Supersymmetry, one of the most popular proposed extensions, predicted that every known particle should have a heavier superpartner. Finding these superpartners would solve several problems at once, potentially explaining dark matter and helping to unify the fundamental forces. But as the LHC began collecting data, those exotic new particles didn't show up. The supersymmetric particles that should have been easy to detect remained conspicuously absent. Searches for other predicted phenomena, like tiny extra dimensions of space or exotic new forces, came up empty. The Standard Model kept passing every test. By the time the Higgs boson was discovered in 2012, confirming the last missing piece of the Standard Model, some physicists were beginning to worry. What if the Standard Model was all there was? What if nature had no new surprises in store at the energy scales the LHC could probe? This concern deepened as the LHC continued to run, colliding protons together billions of times per second, generating staggering amounts of data, and finding nothing beyond what the Standard Model predicted. Oh, there were occasional hints of something interesting, small statistical fluctuations that might have indicated new particles or new forces. But as more data accumulated, these hints invariably faded away, revealing themselves as nothing more than random statistical noise. The universe seemed stubbornly determined to behave exactly as the standard model said it should. But then, gradually, subtly, a different pattern began to emerge. It wasn't dramatic. There were no sudden, obvious discoveries of new particles or forces. Instead, physicists noticed small discrepancies in how certain particles behaved, deviations from standard model predictions that were individually modest, but which, taken together, began to paint an intriguing picture. These weren't the random statistical fluctuations that had appeared and disappeared before. These anomalies persisted as more data was collected. They showed up in multiple different types of experiments. And most importantly, they all seemed to point in the same direction, suggesting not just random errors, but a systematic difference between how particles actually behave and how the standard model says they should. The most tantalizing of these anomalies involves particles called muons and their strange, unexpected behavior in magnetic fields. Muons are essentially heavy versions of electrons, identical in every way, except that they're about 200 times more massive. According to the standard model, this mass difference should be the only significant distinction between electrons and muons. All the fundamental forces should treat them identically otherwise, a principle physicists call lepton, universality. When a muon is placed in a magnetic field, it precesses, meaning it wobbles like a spinning top that's starting to fall over. The rate of this precession, called the muon's magnetic moment, can be calculated with extraordinary precision using the standard model. This calculation is enormously complex, involving contributions from every particle and force in the standard model, including virtual particles that briefly pop in and out of existence in the quantum foam that underlies reality. Despite this complexity, physicists have managed to calculate the theoretical prediction to incredible accuracy. Experimentally, measuring the muon's magnetic moment is equally challenging. It requires creating beams of muons, which are unstable and decay in microseconds, and measuring how they precess in carefully controlled magnetic fields. This experiment was first done decades ago at Brookhaven National Laboratory and has recently been repeated with greater precision at Fermilab. Both experiments found the same puzzling result. The measured magnetic moment differs from the standard model prediction by a tiny but significant amount, about 2 parts in a million. Now, 2 parts in a million might not sound like much, and in everyday life, it isn't. But in particle physics, where theoretical predictions and experimental measurements routinely agree to better than 1 part in a billion, a discrepancy of 2 parts in a million is enormous. It's like predicting someone's height to the nearest millimeter and being off by several centimeters. Something is clearly wrong either with the measurement, the calculation, or the standard model itself. The measurement has been checked and rechecked. The experiment has been repeated at different laboratories. The result holds up. The theoretical calculation has been scrutinized by dozens of research groups using different computational methods. Some calculations confirm the discrepancy. Others, using newer techniques, suggest the standard model might actually predict a value closer to what's observed. The situation remains controversial, with heated debates in the physics community about which calculations to trust. But the possibility remains that we're seeing genuine evidence of new physics, of particles or forces not included in the standard model that contribute to the muon's magnetic moment. What could these hypothetical new particles or forces be? One possibility is that there are additional Higgs-like bosons beyond the one discovered in 2012. The standard model includes only one Higgs boson, but many proposed extensions of the model predict multiple Higgs particles with different masses and properties. These additional Higgs bosons could interact with muons in ways that slightly alter their magnetic moments. Alternatively, the anomaly could be explained by new force-carrying particles similar to photons or W and Z bosons, but belonging to forces we haven't discovered yet. Or it could be evidence of supersymmetric particles. the heavy superpartners that failed to show up in direct searches, but which might still exist and could contribute to the muon magnetic moment through subtle quantum effects. The muon anomaly isn't the only crack appearing in the Standard Model's foundation. CERN experiments have also uncovered puzzling behaviors in how certain particles decay, transformations that seem to violate the principle of lepton universality. When unstable particles break apart, the Standard Model predicts they should decay into muons and electrons at equal rates. But measurements of certain decays of B mesons, particles containing bottom quarks, show them decaying into electrons more often than into muons, in apparent violation of this fundamental principle. Again, the effect is small, but it's persistent and shows up in multiple different decay processes. The statistical significance has grown as more data has been collected, making it increasingly unlikely to be just a random fluctuation. If confirmed, this would be clear evidence that the forces governing particle interactions treat muons and electrons differently in ways the Standard Model doesn't account for, pointing toward new physics beyond our current understanding. These anomalies in B meson decays are particularly interesting because they seem related to the weak nuclear force, one of the fundamental forces described by the Standard Model. In the Standard Model, the weak force is mediated by W and Z bosons, which interact identically with all types of leptons. But if there are additional force-carrying particles, perhaps heavier versions of the W and Z bosons, or entirely new types of gauge bosons, they might interact differently with muons and electrons, explaining the observed deviations. Theoretical physicists have proposed numerous models that could explain these anomalies, introducing new particles or forces in various configurations. Some of these models predict leptoquarks, hypothetical particles that can transform quarks into leptons or vice versa, which could mediate new types of interactions between matter particles. Others invoke Z-prime bosons, heavy cousins of the Z boson that could carry a new fundamental force. Still others suggest modifications to how the Higgs mechanism works, introducing new scalar particles that couple differently to different types of leptons. What makes these anomalies so exciting is that they're appearing in different types of experiments, but could potentially be explained by the same new physics. If the same new particles or forces that cause the muon magnetic moment anomaly also cause the violations of lepton universality in B meson decays, that would be strong evidence that we're not just seeing random errors, but genuine signs of a deeper level of reality beneath the Standard Model. Physicists are actively looking for such connections, trying to construct unified theories that explain multiple anomalies simultaneously. Meanwhile, CERN experiments continue to probe other frontiers where the Standard Model might crack. One particularly important area involves the Higgs boson itself. While the discovery of the Higgs was a triumph for the Standard Model, confirming its final missing piece, physicists are now studying the Higgs in minute detail, looking for any deviations in its properties from Standard Model predictions. How often does it decay into different types of particles? How strongly does it interact with quarks, leptons, and other bosons? Does it have any unexpected decay modes into particles we haven't discovered yet? So far, the Higgs seems to behave almost exactly as predicted, but almost isn't good enough. Physicists are measuring its properties with ever-increasing precision, knowing that even tiny deviations could point toward new physics. For instance, if the Higgs decays into dark matter particles, those decays would be invisible to detectors, showing up only as an apparent deficit in the rate of visible decays. Finding such a deficit would be direct evidence of dark matter, and would revolutionize our understanding of what makes up most of the universe's mass. Another frontier involves the search for rare processes that the Standard Model predicts should happen, but which are so unlikely that they've never been observed. For example, the Standard Model allows certain particles to decay through processes involving multiple weak force interactions happening simultaneously, which is so improbable that it might happen only once in trillions of decays. Observing such rare processes would test the Standard Model in entirely new regimes. Finding them to occur more often than predicted would suggest new particles or forces are contributing, opening another crack in the theoretical edifice. The challenge with studying these rare processes is statistical. When you're looking for something that happens only once in a trillion times, you need to collect trillions of events to see it even once. This requires running experiments for years, accumulating massive datasets, and developing sophisticated analysis techniques to distinguish the tiny signal you're looking for from the overwhelming background of more common processes. It's like searching for a specific grain of sand on an entire beach, except the beach keeps getting new sand added to it every second. This is where the sheer scale of CERN's operations becomes crucial. The Large Hadron Collider doesn't just collide a few particles and call it a day. It collides bunches of protons containing billions of particles each, and it does this 40 million times per second. Each collision is recorded by detectors containing hundreds of millions of individual sensor elements, generating data at a rate that would overwhelm any conventional computing system. The amount of data produced in a single year of LHC operations exceeds the total data storage capacity of most countries. Processing and analyzing this flood of information requires some of the most advanced computing infrastructure on the planet. CERN pioneered the development of grid computing, distributing data analysis across thousands of computers at hundreds of institutions worldwide. Scientists had to develop new algorithms and machine learning techniques capable of sifting through petabytes of data to find the rare, interesting events buried within. In many ways, the computational challenges posed by modern particle physics have driven innovation in data science that has found applications far beyond physics, influencing everything from medical imaging to financial modeling to artificial intelligence. But even with all this computational power, discovering new physics isn't simply a matter of collecting enough data. You also need to understand your detector well enough to trust the measurements it's making. Every detector has biases, inefficiencies, and systematic uncertainties that must be carefully characterized and accounted for. A signal that looks like new physics might actually be an artifact of how the detector responds to certain types of particles, or it might be caused by subtle calibration errors, or it might result from mismodeling the background processes you're trying to distinguish your signal from. This is why physicists are extraordinarily careful about claiming discoveries. When you're searching for tiny deviations from expected behavior, you need to be absolutely certain that what you're seeing is real and not some experimental artifact or statistical fluke. The standard threshold for claiming a discovery in particle physics is 5 sigma, meaning the probability that your signal is just a random statistical fluctuation is less than 1 in 3.5 million. This stringent requirement exists because of painful historical lessons where apparent discoveries at lower significance levels turned out to be nothing but noise. The anomalies emerging from CERN haven't yet reached the 5 sigma threshold required for a definitive discovery, but they're approaching it, sitting in what physicists call the tension region between 3 and 4 sigma. At this level of statistical significance, the results are too strong to dismiss as random chance, but not quite strong enough to claim a definitive discovery. This is simultaneously the most exciting and most frustrating place to be in experimental physics. You can see something interesting happening, something that doesn't fit the established theory, but you can't yet be certain whether it's real or will evaporate like so many previous hints of new physics. What gives physicists hope that these current anomalies might be real is their persistence and coherence. Unlike previous hints that came from single measurements and disappeared when more data was collected, these anomalies show up across multiple independent experiments, using different techniques to measure different properties of particles. The muon magnetic moment anomaly appears in experiments at both Brookhaven and Fermilab. The violations of lepton universality appear in multiple different B-meson decay modes measured at CERN. When multiple independent measurements point in the same direction, it becomes increasingly unlikely that they're all just statistical fluctuations. Moreover, some of these anomalies have been known for years, and rather than fading away as more data accumulates, they've actually strengthened. The muon magnetic moment discrepancy was first observed decades ago, and each new generation of experiments has confirmed it with greater precision. The B-meson anomalies were first hinted at in data from earlier experiments and have grown more significant as CERN's LHCb experiment has collected more data. This pattern of persistence and strengthening is exactly what you'd expect to see if you were observing genuine new physics rather than experimental artifacts. Still, the physics community remains cautiously skeptical, and for good reason. History is littered with examples of tantalizing hints of new physics that ultimately proved to be nothing. In the 1980s, experiments claimed to have discovered the Higgs boson at a mass of a few GeV, but these signals disappeared with better data. In the early 2000s, various experiments reported anomalies that sparked excitement about supersymmetry, extra dimensions, and other exotic physics. But none of these anomalies survived scrutiny. Even at the LHC itself, there was tremendous excitement in 2015 when a bump appeared in the data at 750 GeV, suggesting a new particle much heavier than the Higgs. For months, theorists churned out hundreds of papers trying to explain what it might be. But as more data came in, the bump vanished completely. These false alarms aren't the result of bad science or sloppy experiments. They're an inevitable consequence of how statistical analysis works. When you're making hundreds or thousands of different measurements, random fluctuations will occasionally conspire to create apparent signals that aren't real. The more measurements you make, the more likely you are to see such fluctuations. This is why the 5 sigma threshold exists, and why physicists are so reluctant to claim discoveries prematurely. But even acknowledging this history of false alarms, there's something qualitatively different about the current set of anomalies. They're not just random bumps in invariant mass distributions, the usual signature of a new particle. Instead, they're systematic deviations in how particles behave, in the precise values of fundamental properties like magnetic moments and decay rates. These deviations fit together in ways that make theoretical sense, suggesting they could all be manifestations of the same underlying new physics. And crucially, they're appearing at multiple experimental facilities using completely different techniques, making it unlikely they all stem from the same systematic error. The theoretical community has responded to these anomalies with a surge of activity, proposing new models and extensions of the standard model that could explain the observations. Some of these proposals are conservative, adding just a few new particles or interactions to the existing framework. Others are more radical, suggesting that the anomalies are evidence of entirely new symmetries or dimensions of space that we haven't previously suspected. The challenge is that with only a few anomalies to work with, there are many possible theoretical explanations, and it's difficult to determine which, if any, is correct without more data. One particularly intriguing possibility is that the anomalies are connected to the mystery of dark matter. Most proposed extensions of the standard model that attempt to explain dark matter also predict new particles and forces that could contribute to the muon magnetic moment or affect B-meson decays. If this connection is real, then the anomalies at CERN might be our first indirect evidence of the dark matter particles that make up most of the universe's mass. This would be an extraordinary development, linking two of the biggest mysteries in physics, the incompleteness of the standard model and the nature of dark matter, through a common solution. Another possibility is that the anomalies are pointing towards supersymmetry, the elegant theoretical framework that predicts every known particle has a heavier superpartner. While direct searches for supersymmetric particles at the LHC have come up empty, this doesn't necessarily rule out supersymmetry. It could be that the superpartners are heavier than the LHC can directly produce, but they still exist and contribute to processes like the muon magnetic moment through virtual effects. The anomalies could be our first glimpse of supersymmetry, even though we haven't yet produced superpartners directly. Yet another intriguing direction involves leptoquarks, hypothetical particles that bridge the gap between quarks and leptons. In the standard model, quarks and leptons are completely separate types of matter that don't transform into each other. But in many grand unified theories that attempt to unify all the fundamental forces at extremely high energies, quarks and leptons are actually different manifestations of the same underlying entities. And leptoquarks are the particles that mediate transformations between them. If leptoquarks exist at accessible energies, they could explain both the muon anomalies and the B meson decay violations in a unified framework. The theoretical landscape is rich with possibilities, but moving from speculation to certainty requires more data. This is why CERN's experimental program is so crucial. The Large Hadron Collider is currently in the midst of a major upgrade program that will dramatically increase the rate at which it collides particles, allowing experiments to collect much larger datasets. This high luminosity LHC, scheduled to begin operations in the late 2020s, will collide particles at a rate 10 times higher than the current LHC, generating correspondingly more data and allowing physicists to measure rare processes with unprecedented precision. With this increased data collection will come the ability to definitively confirm or rule out the current anomalies. If they're real manifestations of new physics, the statistical significance will continue to grow, eventually crossing the 5 sigma threshold and establishing their reality beyond any doubt. If they're just statistical fluctuations or systematic errors, they'll fade away as the data accumulates, just like so many previous hints of new physics. Either outcome will be scientifically valuable, but obviously, the discovery of genuine new physics beyond the standard model would be far more exciting and transformative. Beyond just confirming the anomalies, the high luminosity LHC will also enable direct searches for the new particles that might be causing them. If there are additional Higgs bosons, or new gauge bosons like Z-prime particles, or leptoquarks, the increased collision rate might allow physicists to actually produce these particles directly and study their properties. This would be the ultimate confirmation, transforming indirect hints of new physics into concrete discoveries of new particles and forces. But even as CERN pushes the LHC to higher luminosity, physicists are already thinking about what comes next. The LHC, for all its power, is fundamentally limited by the energy it can achieve. It accelerates protons to energies of 13 tera-electron volts, which is enormous by everyday standards, but still might not be enough to directly produce some of the heavier particles that theoretical models predict. To truly explore the next energy frontier and search for the most massive new particles, we'll need an even more powerful accelerator. Several proposals are on the table for the next generation of particle colliders. CERN has proposed the Future Circular Collider, a machine that would be almost 4 times the circumference of the LHC and could reach collision energies up to 100 tera-electron volts, nearly 10 times higher than the current LHC. China has proposed the Circular Electron-Positron Collider, which would initially operate as a Higgs factory, producing Higgs bosons in enormous quantities to study their properties with exquisite precision before potentially being upgraded to a Hadron Collider with even higher energy than CERN's proposed machine. These future colliders would cost tens of billions of dollars and take decades to build, representing a massive investment of resources. Whether they get built depends not just on scientific arguments, but on political and economic considerations. Governments must be convinced that the potential scientific returns justify the enormous expense. The public must be persuaded that fundamental physics research deserves this level of investment, even when the practical applications aren't immediately obvious. This is where the current anomalies could play a crucial role. If they're confirmed as genuine new physics, they would provide a clear target for future experiments, a specific energy scale where new particles and forces are waiting to be discovered. This would make the scientific case for a next-generation collider much stronger, transforming it from a fishing expedition into a targeted hunt for specific phenomena. The difference between exploring uncharted territory and following a treasure map is profound, both scientifically and in terms of garnering support. But even if the current anomalies fade away, the case for pushing to higher energies remains strong. The standard model's incompleteness is undeniable. Gravity must somehow be incorporated into the quantum framework. Dark matter must have some particle physics explanation. The matter-antimatter asymmetry must have been generated by some mechanism. The universe is telling us there's more to discover. we just haven't found it yet. The question is whether the new physics lies at energy scales we can access with foreseeable technology, or whether it's hidden at energies so high that we'll never be able to reach them directly. This question gets at one of the deepest issues in contemporary physics, the problem of naturalness. Many of the quantities in the Standard Model seem bizarrely fine-tuned, taking values that appear arbitrary and which require delicate cancellations between different contributions to make sense. The Higgs boson mass is the most famous example. Quantum corrections should make the Higgs enormously heavy, but somehow all these corrections almost perfectly cancel, leaving the Higgs with a mass of 125 GeV, which is relatively light on particle physics scales. This fine-tuning bothers physicists because it seems unnatural, like the universe is conspiring to make certain quantities come out just right. Historically, whenever physicists encountered fine-tuning problems, they've discovered new physics that explained away the fine-tuning by introducing new symmetries or mechanisms. This is why supersymmetry became so popular. It provides a natural explanation for the Higgs mass by introducing superpartners whose quantum contributions cancel those of ordinary particles. But supersymmetry hasn't shown up at the LHC, and the fine-tuning problems remain. This has led some physicists to question whether naturalness is actually a reliable guide to new physics. Perhaps the universe simply is fine-tuned, and we need to accept that some quantities take the values they do without deeper explanation. Others argue that we're not thinking about naturalness correctly, that there might be explanations we haven't considered yet. Still, others suggest that the landscape of possible universes is vast, and we happen to live in one where the constants take values compatible with our existence, a selection effect rather than a fundamental principle. These debates about naturalness and fine-tuning aren't just abstract philosophy. They have concrete implications for where we expect to find new physics. If naturalness is a valid principle, new particles should appear at energy scales not too far above those we've already explored, perhaps within reach of the next generation of colliders. If naturalness is misleading us, the new physics could be at arbitrarily high energies, perhaps even at the Planck scale, where quantum gravity becomes important, energies so enormous that we'll never be able to produce them in terrestrial accelerators. The current anomalies at CERN offer a potential resolution to this impasse. If they're real, they indicate that new physics does exist at accessible energy scales, regardless of arguments about naturalness. The new particles responsible for the anomalies might be heavy enough that we haven't produced them directly yet, but they're light enough that their virtual effects show up in precision measurements. This would vindicate the naturalness arguments and provide a roadmap for future experimental programs. Meanwhile, other experimental approaches are pursuing the search for new physics through different channels. While collider experiments try to create new particles directly by smashing known particles together at high energies, other experiments search for rare processes or subtle effects that could reveal new physics indirectly. These include searches for dark matter particles passing through detectors deep underground, experiments looking for violations of fundamental symmetries like charge parity symmetry, searches for electric dipole moments of particles that would indicate new sources of symmetry violation, and tests of gravity at small scales where deviations from Einstein's theory might appear. Each of these experimental approaches has complementary strengths and weaknesses. Colliders can produce and study new particles directly if they're light enough, but they're blind to particles that interact too weakly or that are too heavy to produce. Dark matter direct detection experiments can find weakly interacting particles that colliders might miss, but only if those particles happen to scatter off atomic nuclei occasionally. Precision measurements of rare processes can reveal virtual effects of particles too heavy to produce, but interpreting the results often requires theoretical assumptions. The power of this multi-pronged approach is that discoveries in one area can inform and guide searches in others. If CERN's anomalies are confirmed and attributed to specific new particles, this tells dark matter experiments what to look for and tells precision measurement experiments which additional processes to study. Conversely, if dark matter experiments detect a signal, This provides information about the properties of dark matter particles that can guide collider searches. The different experimental programs aren't competing but collaborating, each contributing pieces to the larger puzzle. This collaborative approach extends globally, with experiments at facilities around the world all working toward the common goal of understanding nature's fundamental laws. Beyond CERN in Europe, there's Fermilab in the United States, where the muon G-2 experiment is measuring the muon magnetic moment with unprecedented precision. There's Keck in Japan, home to the Belle 2 experiment studying B meson decays in ways complementary to CERN's LHC experiment. There are neutrino experiments in multiple countries trying to understand these ghostly particles and their mysterious properties. There are dark matter detectors in laboratories scattered across the globe, from deep mines to Antarctic ice. The international nature of this scientific enterprise reflects both the complexity of the questions being addressed and the extraordinary cost of the experiments required to answer them. No single nation can afford to explore all frontiers of particle physics simultaneously, so countries pool resources, share expertise, and divide responsibilities. Scientists move freely between institutions. Data is shared openly, and discoveries belong to the entire scientific community rather than to individual nations or laboratories. In an era of increasing geopolitical tensions, particle physics remains one of the last truly global collaborative endeavors. This collaboration extends beyond just building and operating experiments. Interpreting the results requires sophisticated theoretical frameworks that draw on insights from quantum field theory, general relativity, cosmology, and pure mathematics. Theorists and experimentalists work in close partnership, with theorists proposing new models and predictions that experimentalists test, and experimental results inspiring theorists to develop new frameworks. The interplay between theory and experiment has driven physics forward for centuries, and it remains as vital today as ever. The current situation, with tantalizing hints of new physics emerging from multiple experiments but no definitive discoveries yet, creates a particular dynamic in this theory-experiment dialogue. Theorists must balance caution with creativity, developing models that could explain the anomalies without overfitting to what might turn out to be statistical fluctuations. Experimentalists must balance the excitement of potentially paradigm-shifting discoveries with the skepticism necessary to avoid claiming false positives. Both communities are acutely aware that premature claims can damage credibility and waste resources, but excessive caution can slow progress and miss opportunities. What makes the current anomalies particularly challenging to interpret is that they exist in a realm where both the standard model calculations and the experimental measurements are extraordinarily difficult. Calculating the muon magnetic moment requires summing contributions from countless virtual processes involving every particle in the standard model, including subtle effects from the strong nuclear force that are notoriously hard to compute. Different groups using different computational methods get somewhat different results, leading to debates about which calculations to trust. The strong nuclear force presents special challenges because it's described by a quantum field theory called quantum chromodynamics, or QCD, which behaves very differently from the theories describing the other forces. At high energies, the strong force actually becomes weaker, a property called asymptotic freedom that allows physicists to use perturbation theory to make calculations. But at low energies, the strong force becomes extremely strong, as its name suggests, and particles called quarks and gluons become permanently confined inside composite particles like protons and neutrons. This confinement makes low-energy QCD calculations fiendishly difficult. To handle these difficulties, physicists have developed a technique called lattice QCD, where spacetime is approximated as a discrete grid of points, and the calculations are performed numerically on supercomputers. This approach has become increasingly powerful as computers have grown faster and algorithms have improved, allowing lattice calculations of unprecedented precision. Some recent lattice QCD calculations of the muon magnetic moment suggests that the standard model prediction might actually be closer to the experimental value than earlier calculations indicated, potentially eliminating the anomaly altogether. However, other physicists question whether these lattice calculations are fully reliable, pointing to potential systematic uncertainties that might not be adequately accounted for. There are also alternative approaches using experimental data on particle collisions to constrain the QCD contributions, and these approaches tend to support the existence of a discrepancy between theory and experiment. The resulting controversy highlights a fundamental challenge in modern physics. As calculations and measurements become more precise, correctly estimating uncertainties becomes increasingly crucial and increasingly difficult. This situation creates an interesting epistemological problem. We're trying to determine whether an anomaly is real, but doing so requires comparing a measurement to a theoretical prediction, both of which are subject to uncertainties that are themselves uncertain. How confident should we be in claiming a discovery when both sides of the comparison involve complex systematic uncertainties that different experts evaluate differently? There's no simple answer, which is why the physics community relies on extensive peer review, independent cross-checks, and ultimately, the accumulation of multiple independent pieces of evidence, all pointing in the same direction. The experimental side faces its own set of challenges. Modern particle detectors are marvels of engineering, containing millions of individual sensor elements that must work together with exquisite precision. But they're also extraordinarily complex systems with countless potential sources of systematic error. Particles passing through the detector interact with the material in ways that must be carefully modeled. Electronic readout systems must function flawlessly, even in the harsh radiation environment near a particle collision point. Calibration must account for how detector responses change over time as components age or radiation damage accumulates. Understanding and controlling these systematic effects requires years of painstaking work. Physicists perform countless calibration measurements using known particles and processes to map out how their detectors respond. They develop detailed simulations that model every aspect of how particles interact with detector materials. They design cross-checks and consistency tests to verify that their measurements are robust against various possible sources of error. This unglamorous work doesn't make headlines, but it's absolutely essential to ensuring that discoveries are real and not artifacts of instrumental effects. The fact that multiple independent experiments are seeing consistent anomalies is reassuring precisely because each experiment has its own unique, systematic uncertainties. If the LHCb experiment at CERN and the Belle 2 experiment in Japan both measure violations of lepton universality and B-meson decays, and their results agree, despite using completely different detector designs and analysis techniques, it becomes much harder to attribute the results to experimental artifacts. Similarly, if the Brookhaven and Fermilab muon experiments, separated by decades and using different detector technologies, both find the same discrepancy in the muon magnetic moment, this strengthens confidence in the result. Yet even with multiple confirming experiments, physicists remain cautious. The history of particle physics includes examples of correlated errors, where multiple experiments made the same mistake because they relied on common assumptions or techniques. There have been cases where theoretical calculations contained subtle errors that weren't caught for years because everyone used the same approach. Vigilance against such possibilities is part of the scientific culture, a healthy skepticism that guards against wishful thinking and confirmation bias. As data accumulates and analyses become more sophisticated, the picture should gradually clarify. If the anomalies are real, the statistical significance will continue to grow, and eventually, direct evidence of the new particles causing them should emerge. If they're not real, the discrepancies will diminish as systematic effects are better understood and controlled. We're in a period of transition, moving from hints and tensions to definitive knowledge, and while this transition can be frustratingly slow, it's the only reliable path to truth. The implications of confirming new physics beyond the standard model would be profound and far-reaching. At the most basic level, it would represent the first fundamental extension of our understanding of particle physics in over 50 years. The Standard Model was largely completed by the mid-1970s, with subsequent decades spent testing and confirming its predictions rather than discovering genuinely new phenomena. Finding physics beyond the Standard Model would open entirely new chapters in our understanding of nature's fundamental laws. More specifically, discovering the particles responsible for the current anomalies would provide crucial clues about how to extend the Standard Model and what lies beyond it. The properties of these new particles, their masses, their interaction strengths, how they fit into larger symmetry structures, all of this information would constrain theoretical models and point the way toward a more complete theory. It would be like finding new pieces of a jigsaw puzzle that suddenly make the overall picture clearer. The discovery could also revolutionize our understanding of cosmic history. The laws of particle physics operating in the early universe determined how matter formed, how structures emerged, and ultimately how conditions arose that allowed life to exist. If there are additional particles and forces beyond what the Standard Model describes, they could have played crucial roles in cosmic evolution. They might have generated the matter-antimatter asymmetry that allowed matter to survive. They might constitute the dark matter that shaped the formation of galaxies. They might have influenced the expansion history of the universe in ways we haven't appreciated. Understanding these cosmic connections requires not just discovering new particles and accelerators, but also working out their cosmological implications. This involves complex calculations of how these particles would have behaved in the extreme conditions of the early universe, how they would have interacted with ordinary matter and radiation, what relics they might have left behind. It requires collaboration between particle physicists, cosmologists, and astrophysicists, each bringing their own expertise to bear on different aspects of the problem. The technological impact of fundamental physics discoveries, while often unpredictable, has historically been enormous. When J.J. Thomson discovered the electron in 1897, nobody could have predicted that this discovery would eventually enable everything from computers to telecommunications to medical imaging. When physicists developed quantum mechanics in the early 20th century to explain atomic behavior, they weren't thinking about lasers, or transistors, or MRI machines. Yet all of these technologies emerged from that fundamental understanding. When CERN developed the World Wide Web in the 1980s as a tool for particle physicists to share data, they had no idea it would transform human civilization. The technologies developed to enable particle physics research often find applications far beyond physics. The development of superconducting magnets for particle accelerators has led to improvements in MRI scanners used in medicine. The radiation detection techniques pioneered in particle physics experiments have found applications in medical imaging and cancer treatment. The data analysis methods and computational infrastructure developed to handle the enormous datasets from collider experiments have influenced how we approach big data problems in fields from genomics to climate science to artificial daughter. Intelligence? Beyond specific technologies, fundamental physics research drives innovation in education and workforce development. The technical challenges of building and operating experiments, like those at CERN, push engineers and scientists to develop new skills and expertise. Graduate students and postdoctoral researchers working on these experiments gain experience with cutting-edge technologies and analytical methods that they carry into other fields. Many of the scientists and engineers who worked on particle physics experiments have gone on to leadership roles in technology companies, national laboratories, and academic institutions, applying the problem-solving approaches they learned in fundamental research to practical challenges. There's also an intangible but vitally important cultural impact of fundamental physics research. Human civilization has always looked to the frontiers of knowledge, driven by curiosity about how the universe works and our place within it. The questions particle physics addresses: what is matter made of? How did the universe begin? What are the fundamental laws governing reality? Are among the deepest and most profound questions humans can ask. Even for people who will never directly work with particle accelerators or quantum field theories, knowing that we're actively exploring these questions, that we're not simply accepting ignorance, but pushing to expand human knowledge, provides meaning and inspiration. This cultural dimension becomes particularly important when considering the investment required for future particle physics facilities. The scientific case for building a next-generation collider is strong, but so is the price tag. In a world facing challenges like climate change, disease, poverty, and inequality, is it justifiable to spend tens of billions on a machine to study fundamental particles? Different people answer this question differently, reflecting different values and priorities. The case for fundamental research rests partly on its track record of unexpected applications and technological spin-offs, but also on the principle that expanding human knowledge is intrinsically valuable, that understanding nature is a worthy goal in itself. We don't demand that art or music or literature justify their existence through practical applications. We recognize them as fundamental aspects of human culture that enrich our lives and help define who we are. Fundamental science occupies a similar cultural space, representing humanity's systematic effort to understand reality through observation, experimentation, and reason. Moreover, the choice isn't really between funding particle physics and solving other problems. The resources required for a next-generation collider, while large in absolute terms, are tiny compared to global military spending or even corporate research budgets in some industries. The United States alone spends more on air conditioning its military bases than the entire global particle physics community spends on all research. Framing the debate as fundamental physics versus addressing practical problems creates a false dichotomy, as if we must choose one or the other, when in reality, we have resources for both. That said, the particle physics community must make a compelling case for continued investment, explaining clearly what questions we're trying to answer, why they matter, what we might discover, and what we might learn even if we don't discover what we're looking for. The current anomalies, if confirmed, provide exactly this kind of compelling case, a clear indication that there's something beyond the standard model waiting to be discovered at accessible energy scales. This is why so much attention is focused on understanding whether these hints of new physics are real. As we await more data and more precise measurements, the particle physics community is also engaged in extensive planning and debate about the optimal path forward. Should we prioritize building a higher energy hadron collider to directly produce new heavy particles? Or would we learn more from a precision electron-positron collider that could study the Higgs boson and other particles in exquisite detail? Should we focus on upgrading existing facilities like the LHC, which we know work and which have proven track records? Or should we invest in entirely new experimental approaches? These questions don't have obvious answers. Different approaches have different strengths and address different aspects of the physics. A high-energy hadron collider could discover very massive new particles and probe physics at energy scales we've never accessed before. A precision electron-positron collider might not reach as high energies, but it would produce much cleaner experimental conditions, making it easier to study subtle effects and rare processes. Upgrading existing facilities is less expensive and risky than building entirely new ones, but it's also more limited in what new capabilities it can provide. The decision about which path to pursue will ultimately be made by a combination of scientific considerations, technical feasibility, cost, and political will. It will involve negotiations between governments, funding agencies, scientific institutions, and the broader public. It will require making difficult choices about priorities and timelines, balancing the desire to move quickly against the need to design experiments that will remain at the forefront for decades. It's a complex, messy process that doesn't always optimize for what's scientifically ideal, but it's the process by which big science projects actually happen in the real world. Throughout all of this planning and debate, the fundamental questions remain constant. What is the universe made of? How does it work at the most basic level? Are there particles and forces we haven't discovered yet? How do the pieces fit together into a coherent, theoretical framework? These aren't new questions. Humans have been asking them for millennia, but we now have the tools to actually answer them through experiment and observation rather than pure philosophy. The Standard Model represents our current best answer, a remarkably successful theory that explains an enormous range of phenomena with elegant mathematical precision. But it's clearly incomplete, unable to explain dark matter, dark energy, the matter-antimatter asymmetry, neutrino masses, or gravity itself. The cracks appearing in its foundation, the anomalies emerging from CERN and other experiments, might be showing us the way forward, pointing toward a deeper, more complete understanding of reality. Whether these anomalies prove to be real discoveries or statistical flukes, whether they lead us to supersymmetry or leptoquarks or something nobody has imagined yet, whether the path forward requires building massive new facilities or finding clever new ways to use existing ones. One thing is certain, the search will continue. Humans are driven to understand, to question, to explore. We won't stop probing the fundamental nature of reality just because it's difficult or expensive, or because the answers might not have immediate practical applications. CERN's discovery of these potential cracks in the Standard Model reminds us that for all we've learned, we still don't fully understand the universe we inhabit. We've mapped out some of the terrain, identified some of the key players, worked out some of the rules governing their interactions. But the map remains incomplete, with vast territories marked "Here be dragons," where our understanding fails and new physics awaits discovery. The next few years will be crucial in determining whether the current anomalies represent genuine new physics or are ultimately explained within the Standard Model framework. More data from the high luminosity LHC, more precise theoretical calculations using improved computational methods, more measurements from complementary experiments around the world, all of this will gradually resolve the current uncertainties. The scientific process moves methodically, carefully, checking and rechecking results, but it does move forward. And when the picture finally clarifies, when we know whether these cracks are real or illusory, we'll have learned something profound either way. If they're real, we'll have discovered the first evidence for physics beyond the Standard Model, opening new frontiers of exploration and understanding. If they're not real, we'll have tested the Standard Model more stringently than ever before, confirming its validity in new regimes and sharpening our understanding of where the boundaries of current knowledge truly lie. Either outcome advances human knowledge. Either outcome brings us closer to understanding the fundamental nature of reality. Either outcome represents progress in humanity's oldest and most profound quest to comprehend the universe and our place within it. The cracks CERN has found, whether they widen into chasms revealing entirely new physics or narrow into confirmation of what we already know, are taking us forward on that eternal journey of discovery. As we stand at this moment of uncertainty and possibility, with tantalizing hints of new physics emerging from the world's most powerful particle accelerator, we're reminded of both how far we've come and how much remains to be discovered. We've split the atom, found the Higgs boson, explained the forces governing particle interactions with mathematical precision. Yet we still don't know what makes up most of the universe, how gravity fits into the quantum framework, or whether the fundamental laws we've discovered represent the deepest level of reality, or merely another layer to be peeled back. The search for answers continues, driven by human curiosity, enabled by human ingenuity, pursued by a global community of scientists dedicated to understanding how nature works. The machines we've built, the theories we've developed, the experiments we've designed, they're all tools in service of this fundamental quest. And as those tools become more powerful, as our measurements become more precise, as our theoretical frameworks become more sophisticated, we move closer to glimpsing what lies beyond our current understanding. The universe holds its secrets closely, revealing them only to those willing to look carefully, think deeply, and question relentlessly. CERN's discovery of anomalies in the Standard Model suggests we're on the verge of another revelation, another step forward in our understanding. Whatever we ultimately find, the search itself ennobles us, representing the best of what humans can achieve when we turn our attention to the deepest questions about existence itself.